Today we're plunging into the fascinating world of brain signals.
Yeah, and we're using a source that describes a specific tool, an advanced EEG signal simulator.
Okay, so let's unpack this then. What's our goal here? What are we trying to figure out?
Well, the mission is really to get a handle on what these EEG signals actually are, how they're, put together from their basic parts.
And what gets in the way, like noise and stuff?
Exactly, interference,
Mm-hmm.
what messes up clean recordings, and critically, how a tool like this simulator we're looking at helps us learn about these really complex waveforms.
Because, I mean, think about it. Our brains are constantly going all this electrical activity.
Nonstop.
And being able to measure that, understand it, that seems absolutely key for insights into like different cognitive states, right?
Mhm.
Or diagnosing neurological problems.
Or even just grasping general brain function on a deeper level. It's fundamental.
Right.
And that's really where a simulator like the one in our source comes into play. It lets us generate a synthetic signal.
Synthetic, like artificial.
Yeah. Basically an artificially created waveform, but one that mimics the characteristics of real brain activity.
How does it do that?
Well, the source explains it lets you combine the fundamental brain waves, delta, theta, alpha, beta, and then, crucially, it lets you add in common types of noise, artifacts, they call them.
Ah, artifacts. Okay,
Yeah.
so instead of just getting this like messy real-world recording,
Which can be really chaotic, yeah.
this tool lets you build the signal piece by piece. See the components.
Exactly. You can isolate things, see how they interact. So, whether you're just curious about this stuff or maybe you need to get the basics down quickly.
This deep dive should give you that foundation.
Right. And what's really interesting, as the source points out, is how this kind of tool serves, well, two main groups.
Oh.
For someone new to EEG, it's like an intuitive playground. You tweak things, see the results instantly, helps build that gut feeling for how it works.
Makes sense. Learn by doing.
But then for someone more experienced, maybe, say, an engineer developing signal processing algorithms, it's a reliable utility.
How so?
Because you have this controllable, predictable signal, you know exactly what went into it, so you can test your algorithms maybe for filtering out that noise we mentioned, or even for developing brain-computer interfaces.
Gotcha. A controlled test bed. So, based on the source, how is this thing actually structured? How does it work?
So it describes the application as being split, basically. Control panels on one side, where you set everything up, configure the signal,
Okay.
and visualizations on the other side, where you see the results. You change something in the controls.
And the graphs update immediately.
Dynamically, yeah. So on that control side, there are a few key sections that really help illustrate how we characterize brain signals. First, brain state presets.
Presets, like pre-configured settings.
Exactly. And this is super helpful because, as the source notes, different mental states tend to correlate with different patterns of brainwaves.
Oh, right. Like being relaxed versus focused.
Precisely. So you might select relaxed meditative, and the simulator automatically boosts the alpha wave amplitude that's typically strong, around 8 to 12 hertz when you're relaxed but awake. It's a quick way to see a representative signal for a known state.
Ah. Okay, so you don't have to manually guess what a relaxed brain signal looks like. It shows you a typical composition. That's pretty smart.
It really helps connect the states to the signals. And then there's the artifact simulation section. This is so important.
Why is that?
Because, and the source really emphasizes this, real-world EEG is almost always contaminated. You get electrical signals that aren't actually coming from the brain itself.
Right, like muscle movements.
Exactly. The simulator lets you dial in common ones. You can add muscle artifact, that's EMG signal. It shows up as high-frequency noise, kind of spiky, from things like clenching your jaw or even just scalp muscle tension.
Yeah, the source mentions those look like really fast, messy spikes in the data.
Oh, they can totally swamp the brain signals you're trying to see. And then there's eye blink artifact EOG. That shows up differently.
How so?
As large, slow wave spikes, usually below like 1 hertz. It happens because your eye itself has an electrical charge, a dipole, and when you blink, it moves, creating this big voltage shift.
Wow. So being able to simulate these, it really drives home why cleaning up real EEG data is such a big deal. You have to get rid of this stuff first.
Absolutely. It makes you appreciate just how complex those real recordings are and why signal processing is essential.
Okay, so beyond presets and artifacts, what else can you control?
Well, then you have the fine-tune waves control panel. This is where you get really granular. You can adjust the fundamental brainwave components individually.
The delta, theta, alpha, beta waves.
Yep, delta, usually 0.5 to 4 hertz, deep sleep territory. Theta, 4 to 8 hertz, think drowsiness, light sleep, sometimes creativity. Alpha, 8 to 12 hertz, that relaxed wakefulness we mentioned. And beta, 13 to 30 hertz for active thinking, being alert, focused.
And you can just adjust sliders for these.
There's a simple mode, yeah, with sliders to quickly change the relative strength, the amplitude of each band. Easy way to play around.
But the source mentioned a customize mode, too, for digging deeper.
Exactly. In customized mode, you can get really specific. You can set the precise center frequency for a waveband.
Okay.
The bandwidth, like how spread out the frequencies are around that center point, and of course, the amplitude or power for each one.
So you could try and replicate specific findings from a research paper or something.
Precisely. Or just explore how changing just one parameter, like bandwidth, affects the overall look of the signal and its spectrum. Very powerful for understanding the building blocks.
And there was something about spectrum overlays mentioned in the control section, dotted lines.
Right. Those show up on the power spectrum graph, which we'll get to. These overlays represent the sort of theoretical ideal shape of each pure brainwave band you've configured, like the raw ingredient before mixing.
Okay, like the ideal alpha shape, the ideal beta shape.
Exactly. Which leads us nicely into the visualization side. Two main graphs are presented in the source.
Right.
First, the power spectrum. This one's shown in the frequency domain.
Frequency domain, meaning it shows frequencies, not time.
Correct. It's generated by applying a mathematical tool called a Fast Fourier Transform, an FFT, to the raw signal. Think of the FFT as deconstructing the complex signal that changes over time and showing you how much energy or power is packed into each specific frequency. So you see peaks where your dominant brainwaves are. It's absolutely crucial for seeing the underlying frequency components.
Got it. So it tells you what frequencies are strongest in the mix and the other graph.
That's the simulated EEG waveform. This one is in the time domain. It shows the raw composite signal, the voltage just fluctuating up and down over time, typically over like a 5-second window, the source says.
Ah, so that's the trace that looks like the classic brainwave recording.
Exactly. And it's literally the sum of everything you've added, all the individual brainwaves plus any artifacts you dialed in. It's the final mixed signal.
Okay. Now, here's something the source really flag is important. You mentioned those dotted ideal overlays on the power spectrum graph. And then there's the actual computed spectrum, the filled-in blue area from the final mixed signal. The source says they don't line up perfectly, right? Even if you only have one main wave active.
Right. And that's not a glitch. It's actually a really key concept the simulator helps illustrate visually. It's fundamental to how waves work.
Okay, so why don't they match? Why isn't the final spectrum just a perfect stack of those ideal shapes?
It comes down to interference. The source uses a great analogy. Think of that final blue spectrum, the one computed from the waveform, as a cocktail.
A cocktail.
It's made by mixing all your ingredients, delta, theta, alpha, beta, plus any EMG or EOG noise you added. Those dotted overlays, though, they're like looking at one pure ingredient in isolation before it got mixed into the drink.
Okay, I like that. The cocktail analogy works. Things blend. They don't just sit there separately.
Precisely. When you add waves together in the time domain to create that single up and down waveform trace, they interfere with each other constantly. At some points in time, the peaks of different waves might line up. They add together, making a bigger peak. That's constructive interference.
Okay, adding up.
But at other moments, a peak from one wave might align with a trough, a dip from another wave. They partially cancel each other out. That's destructive interference.
Ah, okay, so this adding and subtracting is happening all the time along the waveform.
All the time across the entire signal. So when you then take that final combined interfered with waveform and run the FFT on it to see its frequency components.
The result isn't just those neat ideal curves stacked up.
Exactly. The resulting power spectrum, that blue area, is more complex. It's, lumpy, as the source describes it. It reflects how those pure components actually interacted over time to create the final signal you see.
So the overlays show the ideal ingredients, but the blue area shows the actual cocktail after mixing an interaction.
Perfectly put. The overlays are still super useful. They guide your eye, showing you where the energy should be concentrated based on your settings. But the blue area is the reality of the combined signal's frequency content. The simulator makes this relationship much, much more intuitive.
Yeah, you can see it directly instead of just imagining equations. It shows why the sum of the parts looks different in the frequency domain compared to the time domain.
It really demystifies that link between the raw signal and its frequency breakdown.
Okay, so let's wrap this part up. What does this all mean? We've taken this deep dive into the EEG signal simulator. We understand its purpose, education, algorithm testing.
Right, we looked at its parts. The brain state presets for typical patterns, the artifact simulation super important for understanding real-world challenges like muscle noise, EMG, and eye blinks, EOG.
And the fine-tuning controls.
Mm-hmm.
Simple sliders, but also that customized mode for setting specific frequency, bandwidth, amplitude for each wave, delta, theta, alpha, beta.
Then the visualizations, the power spectrum, using the FFT to show power per frequency. That's the frequency domain view.
And the simulated EEG waveform, the raw signal over time, the time domain view.
And we really hit that key concept why the actual signal spectrum, that blue area, looks different from the ideal overlays.
Right, it's all about signal interference. Constructive and destructive interaction between the waves and the time domain.
Meaning the final frequency breakdown isn't just a simple sum of ideal shapes, it's more complex, like that cocktail analogy. Seeing that visually is a huge takeaway.
Absolutely. And the source also touched on future ideas for a tool like this.
Yeah, some exciting directions. Adding more waveforms like gamma waves, those faster frequencies above 30 hertz, often linked to higher cognitive stuff.
Okay.
Simulating more artifact types, maybe EKG from the heart, or that annoying 50 or 60 hertz hum from power lines.
Oh yeah, that hum gets everywhere.
Definitely. Also, more advanced analysis like spectrograms, which show how the frequency spectrum changes over time. Multi-channel simulation to look at patterns across different scalp locations.
So simulating a whole head of electrodes.
Potentially, yeah. And even maybe importing real-time data. Lots of possibilities.
So ultimately, this simulator, as the source presents it, it's this dynamic learning tool for newcomers, right?
Wow.
But also a practical utility for people already in the field.
Exactly. It makes the complexities of EEG, which can seem pretty daunting, much more intuitive and interactive. It helps bridge that gap between the raw squiggly lines you record and the frequency information hidden inside them.
By letting you build it up yourself and see the connections.
Precisely. It demystifies that relationship.
Which actually leads to a pretty important question to leave you, the listener, with.
Okay.
Given how dramatically these artifacts and just the natural interaction between different brain waves can change the signal we actually see. Change it from those clean, ideal components.
Yeah, in ways we can't always predict perfectly in real life.
Right. So how might that reality influence how we interpret real clinical EEG recordings, where we don't have the luxury of knowing the exact ingredients that went in?
Good question.
And what does that imply for building tools like brain-computer interfaces that need to be really robust and accurate? How do they deal with all that inherent noise and complex interaction to reliably figure out what the brain is actually doing?
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.